Hello everyone. In today's lecture, we will learn how to solve trigonometric equations. Now, trigonometric equations may look a little bit different to you when you look at it for the first time. However, the general process of solving a trigonometric equation will be pretty similar to what you've followed to solve other algebraic equations. For example, we will start by isolating the variable that we need to solve for on one side and move all other terms to the other side. We will have to perform certain manipulations, factoring, simplifying, and so on before we can get the final answer, the final solution. And for the most part, the solution of trigonometric equation would be an angle measure in radians. And it may not be a single solution, it could be multiple solutions for the same variable. So we will go through the different types of trigonometric equations, how to solve them, and we'll work through some examples as well. These are all the different types of equations that we will cover in this lecture. First of all, we'll learn how to find all solutions of a trigonometric equation. Then we will go on to solving equations with multiple angles. Recall that I said that a variable in a trigonometric equation can have several solutions. We'll learn how to solve those types of equation. We will learn how to solve trigonometric equations in quadratic form. A quadratic form would be a second degree equation in the sense that the trigonometric functions will be raised to the power 2. For example, sine squared of x or cos squared of x could be tan squared of x, and so on. So we learn how to solve those types of equations. We will be using factoring to separate different functions in trigonometric equations. We may also have to use identities to solve certain types of equations. Of course, we will learn how to use the calculator to solve trigonometric equations, and then finally we'll solve equations with trigonometric and exponential or logarithmic functions. So trigonometric equations combined with exponential and logarithmic functions will also be addressed in this lecture. Let's talk about what a trigonometric equation is and how it is different from other algebraic equations. A trigonometric equation is an equation that contains a trigonometric expression with a variable such as sine of x. In other words, a trigonometric equation will have one or a combination of the 6 trigonometric functions that we learnt. The values that satisfy such an equation are its solutions. There are trigonometric equations that have no solutions, the same as we've come across when solving algebraic equations. It is possible that an equation may not have any solutions at all. When an equation includes multiple angles, which in many cases trigonometric equations do, the period of the function plays an important role in ensuring that we do not leave out any solutions. So when we are solving an equation in trigonometry and we come up with multiple angles as solution, we have to make sure that we do not leave out any of the solutions, and in that case the period of the function is very important. We will work on the first example to find all solutions of a trigonometric equation. The equation given to us is 5 times sine of x equals 3 times sine of x plus square root over 3. Now, the general process will be the same as you've used to solve algebraic equation. That is, the first step would be to isolate the term with the variable in it, move it to one side and all other terms to the other side, combine terms whenever we can, and so on. So the first step will be to to isolate the function on one side of the equation. The function is sine x, and we see on the left hand side there is 5 times sine of x. On the right hand side there's 3 times sine of x. We'll need to move the 3 times sine of x over to the left hand side, and then we'll have to see if we can combine that and make it a single term. What we do here is we take the 3 times sine of x. To move it to the other side, we subtract 3 times sine of x from both sides, and on the left hand side we end up with minus 3 times sine of x. So it's 5 times sine of x minus 3 times sine of x, which gives us 2 times sine of x on the left hand side. On the right hand side, 3 times sine of x minus 3 times sine of x becomes a 0. We are left with plus square root over 3. So now we've brought it down. We have simplified the equation to 2 times sine of x equals square root over 3. In the next step, we will divide both sides by 2 to just have sine of x by itself. So when we do that, we end up with sine of x equals square root over 3. What we've done is, in the step before, we've divided both sides by 2, and we've ended up with sine of x equals square root over 3 by 2. We will now go on to the next slide to see how to come up with the angle values of x whose sine ratio is square root over 3 by 2. However, before moving on, I just wanted to clarify one thing to you. We can combine terms when it's in this form. 5 times sine of x minus 3 times sine of x can be written as 2 times sine of x. We can subtract 3 from 5 and write it as 2 times sine of x. But if we had an expression which was sine of 5x minus sine of 3x, we cannot write it as sine of 2x. In this case, we cannot combine 5x and 3x. If you go back to what you learned about the sum and difference identities of trigonometric functions, this becomes a sine of alpha minus sine of beta situation, and it can only be simplified, or it can only be worked out using the difference formula for the sine function. Therefore, just be very careful. Please do not try to combine sine of 5x and sine of 3x and write it as something like sine of 2x. That's a common error that happens to new students in trigonometry, but I wanted to alert you to that, not to make that mistake. All right? Let's continue with step 2 for solving for the variable for the equation in example 1. Now, we had an equation to start with which had 3 terms in it. We performed all the algebraic steps to combine like terms and so on, and then isolate the trigonometric function of sine x on the left hand side. On the other side, we have a ratio which is positive square root over 3 by 2. At this point, we are ready to solve for x. X here would be angle measures in radians whose sine function is a positive square root over 3 by 2. Now recall that by the ASTC rule, the sine ratio would be positive in quadrant 1 and quadrant 2. Therefore, the solutions of x would be quadrant 1 as well as quadrant 2 angles within the interval 0, 2 pi. Therefore, the solutions for this equation in the interval 0, 2 pi are pi over 3. Sine of pi over 3 is square root over 3 by 2. And in the second quadrant, sine of 2 pi over 3 is square root over 3 by 2. In addition, we can keep going round and round in circles every 2 pi cycles and come up with an angle measure in quadrant 1 as well as quadrant 2. Therefore, unless an interval is specified, the solutions for this equation would be pi over 3 plus multiple rounds of 2 pi. We write it like this: pi over 3 plus 2 times n times pi. In other words, n times 2 pi. As many cycles of 2 pi we can go around in the xy coordinate plane. And the other one, the second quadrant angle, would be written as 2 pi over 3 plus 2 times n times pi. Right? We'll now work on another example, which is solving an equation with a multiple angle. What we mean by multiple angle is that in our equation, the angle measure given to us will be expressed not just as a single variable. However, the variable will be multiplied by another numerical quantity. It could be a positive or a negative integer value, or it could be a fraction as well. Let's go through the question given to us. It says solve the equation tan of 2x equals square root over 3 for x within the interval 0 and 2 pi, which means that we have to find all solutions for x within the interval 0 and 2 pi. So going back to our equation, it says tan of 2x equals square root over 3. What that means is, for what angle would tangent have a value of square root over 3? Now, the angle measure is expressed as 2x. So 2x represents a single angle measure, a single angle value. Therefore, 2x can be represented or denoted by a single variable, let's say t. So for what value of t would tangent have a ratio of square root over 3? Now, using our knowledge of the special angles, we know that tan of pi over 3 equals square root over 3. Now, pi over 3 in our equation is written as 2x. What we can do in order to solve for x is equate 2x with pi over 3 and then solve for x. It's a simple equation. You have to solve for x, therefore divide both sides by 2. 2x divided by 2 gives us x, and pi over 3 divided by 2 is the same as saying pi over 3 times 1/2. We will end up with a value of pi over 6 for x. And when pi over 6 is multiplied by 2, we will get back pi over 3, and then that will satisfy the equation, correct? Tan of pi over 3 equals square root over 3. So that is how we are going to go about solving the equation. This is just one solution for x. Of course, we have to find other solutions of x within the interval 0 and 2 pi. At this point, however, we have to remember that the period of the tangent function is pi units. What that means is the ratios of the tan function repeat themselves after every pi units. Also, if you recall, by the ASTC rule, tangent is positive not only in quadrant 1 but also in quadrant 3. So I'm going to draw an angle here. Let's say this angle measure in the first quadrant is pi over 3, whose ratio is square root over 3. If we go around pi units, we will get another angle in the third quadrant, which will also have a ratio of square root over 3. And that angle measure would be 4 pi over 3 in the third quadrant. And in this way, we have to go around finding values of x within the interval 0 and 2 pi, going around pi units until we get to a solution for x which is between 0 and 2 pi. Now, another thing to remember is that even though x is within 0 and 2 pi, our angle measure is 2 times x. Therefore, this angle measure 2x will be measured between 0 and 4 pi, right? Again, this interval only applies to x. For the angle measure 2x, you have to multiply the endpoints of the interval by 2. So 0 times 2 would be 0. There's no change there. But 2 pi multiplied by 2 would be 4 pi. Therefore, 2x would be angle values between 0 and 4 pi. You have to understand that logic. All right. So let's go through the steps. It says here, because the period is pi, all solutions for this equation are given by the equation 2x equals pi over 3, which we had done up here. So 2x equals pi over 3 plus n times pi, n being the number of pi units that you go around looking for angles whose tangent ratio would be pi over 3. That's what this expression n times pi means. So if we solve for x, we will divide all the terms by 2. 2x divided by 2 is x. Pi over 3 divided by 2 is pi over 6. And then you have to divide n times pi by 2 as well. So we'll end up with n times pi. Right now, for the first quadrant angle, we haven't gone around pi units. We've just started from the positive x-axis. In the first quadrant, it's 0 cycles that we've made. So n will be 0. So when n equal to 0, then x equals pi over 6 plus 0 times pi divided by 2 equals pi over 6. All right, so x will have a solution of pi over 6 for the first quadrant angle. For the third quadrant angle, that is n equals 1. In other words, when we have made pi units around to get to our third quadrant angle, you have to substitute 1 into n and you will get x equals pi over 6 plus pi over 2 units. So when we complete the addition, we will end up with 2 pi for the value of x, not value of 2x. All right. So again, keep that clear in your head. We are solving for x at this point. X has a value of 2 pi over 3. However, 2 pi over 3 times 2 will give us an angle measure of 4 pi over 3. And tan of 4 pi over 3 will be equal to square root over 3 in the third quadrant. So in the next slide, we will continue this process to find two other solutions of x, which will give us all the values of x within 0 and 2 pi. To continue with finding the other two solutions for x, when n equals 2, x will have a value of 7 pi over 6. We solve for x by plugging in 2 for n, so it's 2 pi divided by 2 added 2 pi over 6 gives us 7 pi over 6. And then finally, when n equals 3, just plug in 3 for n. So it's 3 pi over 2 plus pi over 6. So 3 pi over 2 added to pi over 6 will give us a value of x of 5 pi over 3. And now we have found all the solutions of x within the interval 0 and 2 pi. The solutions are pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3. When we multiply each of these x values by 2, we will get a tangent function of square root over 3 as the answer, and that will have satisfied our equation. We will now work through an example which has a trigonometric equation in quadratic form. The equation given to us is 4 times cos squared x minus 3 equal to 0, and we have to solve for x within the interval 0 and 2 pi. In other words, we have to find all values of x within this interval 0 and 2 pi that will satisfy the equation given. We will solve it like any other quadratic equation. What makes this a quadratic equation? The fact that cos has been raised to the power 2 is what makes it a quadratic equation. We begin with our equation 4 times cos squared x minus 3, and then in the next step we have to start the process of isolating cos of x on one side and move everything else over to the other side. We will begin by moving the term 3 over to the other side. Well, we have a minus 3. When we move that to the right hand side, it will become a plus 3. So in the next step, when we add 3 on both sides, we end up with 4 cos squared x equals 3. The next step would be to divide both sides by 4. We have to get rid of the 4 with cos squared x. Therefore, we divide both sides by 4. We end up with cos squared x equals 3 by 4. And then finally, we have to remove the square from cos of x. In order to do that, we take the square root of both sides. And we end up with cos of x equals plus minus square root over 3 by 4. And once we distribute the radical to both the numerator and the denominator, we end up with plus minus square root over 3 by 2. At this point, we are ready to find the values of x whose cosine ratio will be positive or negative square root over 3 by 2, and that will fall within this period of 0 and 2 pi. So looking up our special angles table, the solutions in the interval 0 and 2 pi would be pi over 6, which is the first quadrant angle, 5 pi over 6 is the second quadrant angle, and it will have a negative ratio, a negative square root over 3 by 2. The third quadrant angle will be 7 pi over 6, and then the fourth quadrant angle will be 11 pi over 6, which will have a positive square root over 3 by 2 as its ratio. So at this point we completed the solving of this equation with solutions for x values within the interval 0 and 2 pi. We will now go over an example which involves equations that work with two different trigonometric functions. It's the same variable x, but it's associated with two different trigonometric functions. The example given to us is sine of x multiplied by tan of x equals sine of x. We have to find solutions of x within the interval 0 and 2 pi that will satisfy the equation. When sine of that particular angle is multiplied by the tan ratio of that same angle, then it will be equal to the sine ratio of x. Now, even before going into the steps of solving this, we can see that we can go back to one of the properties that we had learnt way back in algebra called the identity property of multiplication. When a value is multiplied by 1, you get the answer as the value itself. So any value multiplied by 1 is equal to the value itself, correct? The same will apply here. We have sine of x times tan of x equals sine of x. Therefore, if tan of x is 1, then sine of x times 1 would give us sine of x. Correct? So that's something that you can just think of at the outset, and which will help you later on to verify if we are on the right track or not while we are solving the equation. So let's go through the steps now. We've written out the equation sine of x times tan of x equals sine of x. In the next step, we will be bringing the sine of x on the right hand side over to the left hand side, making the right hand side equal to 0. In other words, we will subtract sine of x from both sides, and what do we end up with? On the left hand side, it's sine of x times tan of x minus sine of x. On the right hand side, it is equal to 0. Now, in the following step, we can factor out the common ratio which is sine of x, correct? And we get sine of x and then within brackets tan of x minus 1. So when we factor out sine of x from both the terms on the left hand side, we'll end up with sine of x as the common factor, and within brackets we have tan of x minus 1, the other side equal to 0. Now when one side is equal to 0 and you have factors on the other side, then you can equate each factor to 0. You can end up with sine of x equal to 0 and tan of x minus 1 equal to 0, and then solve them individually. So that's what's done. In the next step, sine of x is equal to 0 and we'll have tan of x equal to 0 next, but they are first working with sine of x, so let's follow along. So if sine of x equal to 0, we are looking for a value of x whose sine ratio is equal to 0. When x is 0, the sine ratio is 0. Again, you can refer to the special angles table, but by this time you should have it memorized. All right, you should just know it. So when x is 0, sine of x is 0. Sine of 0 is 0. So that's one of the solutions. And again, at x equals pi, sine of pi is equal to 0. Correct? So x equal to 0, x equal to pi would be one set of solutions. The next step would be to work with tan of x minus 1. We'll equate tan of x minus 1 to 0 and then isolate the tan of x and write it as tan of x equals 1. And at this point, go back to what I said at the beginning, that in order to satisfy this equation, the tan of x ratio better be a 1. So that agrees with what we found here, correct? Tan of x equals 1. Now let's recall our special angles table to find out what value of x would make the tan ratio equal to 1. And that would be pi over 4. Tan of pi over 4 equal to 1, and 5 pi over 4, which is a third quadrant angle, would also make tan of x equal to 1. Tan of 5 pi over 4 is equal to 1 as well. Therefore, the solutions of x in the interval 0, 2 pi would be 0, pi over 4, pi, and 5 pi over 4. They've arranged the angle values in increasing order from lowest to highest. All right. This is how we can solve equations using the factoring method on equations with two different functions. We'll now solve a trigonometric equation where we'll need to apply a trigonometric identity in order to solve the equation. The question given to us is cos of 2x plus sine of x equal to 0. That's the equation, but we'll have to find values of x between the interval 0 and 2 pi. We will begin with the equation cos of 2x plus sine of x equal to 0. Now we can immediately recognize that cos of 2x is a double angle identity for cosine. So if we can recall the formula for cos of 2x, we can substitute that for cos of 2x, and that will help us bring the two terms with the same trigonometric function. In other words, we will be able to rewrite this equation using just sine of x instead of two different trigonometric functions. All right, so that's the goal. Now, if you recall, there are three different formulas for cosine. Pick the one which has the sine function in it. So we will use the formula which is 1 minus 2 times sine squared x. That's one of the formulas for the cosine of 2x. The double angle formula for cosine has three different formulas. Pick the one which has sine in it because the goal is to rewrite the equation with the same trigonometric function. So we have replaced cos of 2x with 1 minus 2 times sine squared x plus sine x comes down from the equation above is equal to 0. The next step will be to rearrange the order of the terms on the left-hand side. We want the term with the highest power first, and then the term with the next highest power, followed by the one with the lowest power. So what we end up with is 2 times sine squared x minus sine x minus 1 equal to 0. Now I'm going to just work on the side to explain to you how they came up with positive 2 times sine squared x when there's a negative up above, and then negative sine of x when there's a positive sign above, and same for 1. It's a positive above. How did we end up with a negative sign? So we first rearrange the terms and write it as minus 2 times sine squared x plus sine of x becomes the second term, and then plus 1, and then on the other side we have a 0. We want to get rid of the negative sign which is with the first term, because that would make things a little bit difficult when we get to the factoring part of it, because the next step would be to factor the trinomial here. Alright, so one way of getting rid of the negative sign before the first term is to multiply both sides of the equation by negative 1. When we do that, negative 1 times negative 2 sine squared x would be positive 2 sine squared x plus negative 1 times sine of x is negative. So let's change the positive to a negative sine of x, and then negative 1 times positive 1 is negative 1 equal to, the other side remains a 0 because 0 multiplied by any number is 0. So that's how they came up with what we have, 2 times sine squared x minus sine of x minus 1 equal to 0. The next step would be to factor the trinomial. You should be able to recognize we have a trinomial here on the left hand side. So just like you factor any trinomial in algebra, you'll be factoring this as well. If you find it difficult to work with sine of x in this trinomial, temporarily replace it with a. So replace all sine of x with a and rewrite it as 2 times a squared, 2a squared minus a minus 1, and that may make it easier for you to factor it, but you have to remember to replace the a by sine of x afterwards. All right. So once we perform the factoring, we end up with two factors. One of them is 2 times sine of x plus 1. The other one is sine of x minus 1 equal to 0. So at this point, we will be equating each of these factors with 0 and solving for x step by step. So we have 2 times sine of x plus 1 equal to 0 as one equation. The other equation will be sine of x minus 1 equal to 0. We'll work with the first equation. So 2 times sine of x plus 1 equal to 0. Move the 1 over to the other side. It'll be negative 1, and then divide both sides by 2. It'll give us 2 times sine of x equals negative 1, followed by sine of x equal to negative half once we divide both sides by 2. And we'll end up with x values of 7 pi over 6 and 11 pi over 6. Now, just to remind you, sine function is negative 1/2. The sine function will be negative for angles in the third quadrant and the fourth quadrant by the ASTC rule. Therefore, the solutions for x would be third quadrant angles and a fourth quadrant angle. 7 pi over 6, third quadrant, 11 pi over 6 is the fourth quadrant angle. Now for the other equation, which is sine of x minus 1 equal to 0, we'll end up with sine of x equal to 1. What value of x would make the sine function equal to 1? If you recall from your special angles table that it's a quadrantal angle, pi over 2. When x is pi over 2, sine of pi over 2 will be equal to 1. So that's a quadrantal angle. Therefore, the solutions for x for this equation would be x equals 7 pi over 6, third quadrant angle, 11 pi over 6, fourth quadrant angle, and the quadrantal angle pi over 2. So far, the trigonometric equations that we worked on had to do with special angles and ratios of special angles. Not all equations will be with special angles. Therefore, let's look at an equation now where the angle value will not be special and neither will be the ratio corresponding to it. So the equation given to us is tan of x equals 3.1044, correct to 4 decimal places for an x value between 0 and 2 pi. So this time the x value will not be an angle value which is a special angle. For that we have to use our calculators. Right, so let's go through this step. First, we write the equation tan of x equals 3.1044 in this form. X equals arctan. Tan with a superscript of -1 refers to inverse tan, also called arctan. So x can be written as x equals inverse tan or arctan of 3.1044. And then we have to, of course, take out our calculators and find the x value that corresponds to a ratio of 3.1044 for the tan function. Now, when you are using your calculator, the first thing that you must remember is to make sure that the mode on the calculator is in radians and not in degrees. Otherwise, you will not get the right answer. All right. And then once you use the arctan or the inverse tan button on your calculator for the ratio 3.1044, you will get an x value approximately 1.2592. However, tan of x is positive in quadrants 1 and quadrant 3, correct? Because the ratio that they've given to us is a positive value, and you have to remember that in quadrants 1 and quadrant 3, tan of x is positive. Therefore, in quadrant 1, x will be approximately 1.259 radians, and in quadrant 3, it'll be pi plus, pi being the period of the tangent function. The ratios repeat themselves every pi units. Therefore, pi plus 1.2592 will give us a value of 4.4008 in the third quadrant. Again, you have to use your calculator to perform this calculation. All right? Therefore, the solutions for this equation are x equals 1.259 radians and 4.401 radians. All right. Here's another example of a trigonometric equation which will need the use of a calculator to find the angle measure. The equation given to us is sine of x equals -0.2315, and the angle measure, the solution of x, has to be between 0 and 2 pi interval. The ratio given to us is a negative ratio, and the trigonometric function is the sine function. Sine will have a negative ratio in quadrant 3 and quadrant 4. Therefore, the angle measure that we will find from solving this equation will be a third quadrant and a fourth quadrant angle. We will proceed the same way as we did with the previous example. We will rewrite this equation in inverse form, which is x equals inverse sine or arc sine of -0.2315. However, when we use our calculators, we will first find the arc sine of the first quadrant angle with a positive ratio and then convert it into a quadrant 3 and quadrant 4 angle. Before you proceed on your calculator, make sure that the calculator is set to the radian mode, because the final answer should come out in radians. X would be an angle measure in radians. All right. So again, the process is to find the first quadrant angle, which will have a positive ratio, and then we'll convert that by adding pi units to get to the third quadrant angle, and then again similar way we will find the fourth quadrant angle as well. Therefore, when we use our calculator, we will come up with an x value of 0.2336. However, this is a first quadrant angle. So let me just show you here on the side. I'll draw a first quadrant angle with the sine ratio as positive 0.2315. On your calculators, you will use the arc sine button followed by 0.2315 as the ratio input, and you will get an angle measure of 0.2336, which is really this angle in the first quadrant, 0.2336. However, we are looking for a third quadrant angle because the ratio is negative. The third quadrant angle would be here, which is essentially a straight line on the other side of the first quadrant angle. Therefore, we are essentially looking for this angle in green. This angle from the positive x-axis to the ray in the third quadrant. How do we find it? Just add pi to 0.2336. That will give us the third quadrant angle. So since sine of x is negative in quadrants 3 and 4, and we are looking for angle measures in those two quadrants, for quadrant 3, if we add pi to 0.2336, we'll get a value of 3.3752, which is this angle, this entire angle shown in green. So let's write that. This angle has a measure of 3.3752. For the fourth quadrant angle, the fourth quadrant angle will be a reflection of the first quadrant angle across the positive x-axis here. And this angle between the positive x-axis and the ray in the fourth quadrant is minus 0.2336. However, we are looking for the positive angle in the fourth quadrant. We are looking for this angle in yellow, which is the positive angle in the fourth quadrant. In order to find this angle, we will add 2 pi to negative 0.2336. And that's what's done here. To find the x value in quadrant 4, you add 2 pi to negative 0.2336, and you'll come up with an angle measure of 6.0496. So x in the fourth quadrant is 6.0496. Therefore, as the final solution, the solutions for this equation are 3.3752 and 6.0496, the third quadrant and the fourth quadrant angles respectively. We will now work on a couple of equations which is of a slightly different nature in the sense that the trigonometric functions are combined with exponential and logarithmic functions. The question says solve the equations for x between the intervals 0 and 2 pi, and the equation given to us is e raised to the power sine of x equals 1. Here we see that the trigonometric expression, the trigonometric function sine of x appears as the exponent of base e. In order to solve this equation, we will end up taking the natural logarithms of both sides of this equation. And that's what we do in the next step. We have ln of e raised to the power sine of x equals ln of 1. Now, if you think you've gone a little bit rusty on how to solve logarithmic equations, you may want to go back and review the steps of that and also the rules and the properties of solving logarithmic and exponential equations. Otherwise, it will be difficult for you to follow the steps and solve the equations correctly. We have ln of e raised to the power sine x equals ln of 1. Now ln of 1 will be equal to 0 and ln of e. Now when the logarithmic base is the same as the base of the exponent, then we can write it as sine of x. We can replace the entire expression on the left hand side and write it with the exponent as sine of x equal to 0. Now at this point we are ready to solve for x. We are looking for values of x that will have a sign ratio of 0, and that would be angle measures which are 0 and pi. Correct? These are quadrantal angles. X equal to 0 and x equals pi have sign ratios equal to 0. So that's the final answer here. We have found solutions of x between the interval 0 and 2 pi, which would satisfy the equation e raised to the power sign of x equals 1. Let's look at another example. Again, we need to find solutions for x between the interval 0 and 2 pi. The equation given to us is 3 raised to the power cos x minus square root over 3 equal to 0. Here too, cos of x, the trigonometric function, appears as an exponent. Therefore, let's go through the steps here. We first have to move the constant term, negative square root over 3, to the other side of the equation, which would give us 3 times cos of x equals square root over 3. Now, square root over 3 can be rewritten as 3 raised to the power 1/2. It can be written in exponent form as 3 raised to the power 1/2, and then since both sides have exponents and the same base 3, we can equate the exponents. Again, you have to recall your knowledge of the properties of exponents and solving equations with exponents. As long as they have the same base, the exponents can be made equal to each other. We'll end up with cos of x equals 1/2, and at this point we are looking for values of x whose cosine ratio is 1/2, and we will come up with the inverse cos of 1/2, giving us a value of pi over 3 and 5 pi over 3. Pi over 3 is in the first quadrant, 5 pi over 3 is in quadrant 4, because cosine has positive ratios in quadrant 1 and quadrant 4, right?